Okay, our last speaker for the session is Guillaume Coiffier. He will talk about compactly supported detail field for high-quality neural implicit surfaces.
So, hello everyone. So this talk will be about implicit representations of geometry, where we consider a surface defined as the zero-level set of some continuous function over space. And in particular, we will look at sign distance function that assign the distance to the boundary of the considered object everywhere in space, counted negatively inside of the object and positively outside. So since I am a computer scientist, the first question that comes to my mind is how one could compute such a distance function given an arbitrary object. And if the object is simple enough, and for a collection of simple shapes, there exists closed-form solutions to compute this sign distance function that can be computed in a few lines of code only, but that quickly its limit when the shape becomes more complicated. And in that case, we have to approximate the sign distance function and rely on the oldest trick in the geometry processing book, which is discretization in a tractable space of functions. So there are many such spaces of functions that could be considered, including but not limited to finite elements, where we define a mesh over the domain and compute the value of the function at each of the vertices of the mesh, then interpolate, or the so-called meshless approaches like radial basis functions, or more recently approaches based on neural networks where the function is directly encoded in the parameters of the neural network. So the idea I want to play around with today is to design such spaces of function such that some property is always satisfied. So design the space of functions as a subset of all functions that share a given property, so that when you optimize, this property will always be true by construction. And since we are talking about distance field, the property that we are interested in is the conservativeness of the field. That is to say that we would like our implicit field to always underestimate the true distance to the object. So this boils down to two conditions. The first one is that the zero-level set should match with the boundary of the considered object, and that the function should be one Lipschitz, so always underestimate the true distance. Why do we want these two properties to be true? Well, because if you have a conservative neural distance field, you know that you have the empty sphere property. That is to say, if you take a point in space and draw the sphere of radius, the value of the field at this point, you know that this field does not intersect the zero-level set of your shape. So if you are walking along a ray and you can take steps of size, the value of the field, and you know that you will never intersect the distance, the zero-level set, so you will converge to it and compute intersections with guarantees. On the other hand, if you have a non-conservative field, this sphere centered at any point can intersect the object arbitrarily, and if you want to consider ray marching applications, you may overshoot your projection and nothing can be guaranteed anymore. And as it turns out, computing conservative distance field has already been achieved 2 years ago by Louis Bethune and myself, and we managed that by working in a space of one Lipschitz function defined as neural networks. So we were able to get very regularly spaced level sets and a very regular distance function for our objects, but this robustness came at the cost of geometrical accuracy, because we weren't able to recover the correct level set. We only had a very low detailed representation of it. And this is not a problem of having not enough parameters or not enough gradient steps. Even if you increase those parameter count or the length of the optimization, you still aren't able to converge. And this is a known bias towards low frequency shapes in deep learning using those kind of neural networks. And to counter this bias, some other methods have tried to develop architectures that are able to reconstruct the zero-level set. But this accuracy now comes at the cost of a very irregular level set further away from the surface. So it seems that there is some kind of trade-off between the two conditions that we would like to be true for our representation, so between robustness and accuracy. And the question I'd like to ask is whether it is reasonable for a single function, single representations, to satisfy those two properties, and if it would be reasonable if those two properties could be split into two different functions that would be added to represent our shape. And as it turns out, this is an idea that's already been played around with in a previous work where a base implicit function represented by some siren network was perturbed implicitly by another siren network of higher frequency that would introduce more details into the representation. So here the focus was not on conservativeness, so there is nothing that can be proven on the Lipschitz constant of the total implicit field, but we will take inspiration of that while trying to preserve conservativeness as much as possible. So our approach is the following. So we will first consider some points that will define a shape in space, and we will train a one Lipschitz network onto it to recover some low detail sign distance field. And then we will try to add a perturbation to this sign distance field that only acts locally around the zero level set, so that the total implicit goes precisely through prescribed point. So we will define another field that we will call the detail field that will be defined as a sum of compactly supported radial basis function. I will come back to that in a few minutes. Centered around the points on the surface. And now total implicit function will be the sum of the one Lipschitz field and the detail field. And as I said, this detail field will be fitted, will be optimized so that the sum of the two is zero at all the prescribed point on the surface. That is to say, the detail field completely compensates for the one Lipschitz network, and the zero level set goes exactly where we want it to go. So, as I said, the first step is to train a one Lipschitz network. So for that, there is nothing new. We rely on the method from 2 years ago. So recall that if you are given, if you are given some inside-outside partitioning of an object, you are able to train on a Lipschitz architecture on the Hinge-Kantorowicz-Rubinstein loss, which converges to the sign distance field of the object. So I won't go into very much detail there, so if you have questions, please ask me afterwards. What's more interesting, and what I will tell you more into details, is the design of the detail field. So as I said, it is a sum of compactly supported radial basis functions. So if I take some points x1, xn on the surface of the object, I will define my detail field as a weighted sum of function phi that only depends on the distance from the query point x to the centers xi. And the function we consider is this polynomial, so it's 0 when the distance is larger than some threshold parameter sigma. So this accounts for the fact that our detail field is only defined in some narrow band of with sigma around the zero level set. And as it turns out, having a detail field of this form is very convenient, because the weights that we need to assign to the function phi are uniquely determined by the n constraint that we set. That is to say that we want the detail field to exactly compensate the value of the neural Lipschitz field at the given points on the surface. And if you expand those n constraints, they are linear in the weights wi, so you end up with a linear system that is sparse, because we are using compactly supported basis functions, and also symmetric, so it can be easily solved using some iterative method like the conjugate gradient method. And what remains to be determined is the value of this threshold parameter sigma. So this sigma should be as small as possible, so that the perturbation is as small as possible on our base field, but it should also be large enough so that the perturbation is expressive enough. And in practice, this value will depend on the number of RBFs that we put on the surface, their density, and the total error that is made. So what we did is we considered the maximum error that we measured between some point on the true geometry and the zero level set of the neural network. And we performed the grid search experiment to determine the best sigma, and it turns out that starting from sigma equal this maximal measured error, we get a perfect result, and increasing sigma even further doesn't really increase the quality, and you only get more computational cost in the resolution. So in practice, we take sigma equal 1.1 L. That is the base trade-off between accuracy and speed. So that is basically all there is to it. So basically our idea was to consider one Lipschitz field, add a compactly supported detail field, and that's it. So let's look at some results. And as it turns out, if you look at very detailed meshes, you are able with this method to reconstruct the mesh using like 500,000 RBF centers, which amounts at a very small portion of the total memory that is needed to represent the same geometry as a mesh. And we are able to achieve still quite a good amount of details. So for reference, this was the output of the previous method, so only using the one Lipschitz network, and as you can see, you have no details anymore on this kind of geometry. Perhaps what is more telling is to look at the level set and what's going on further away from the zero level set surface. And as you can see, the level sets are very regular, and they are almost unchanged by the addition of this detail field. So the only level set that changes is the ones that are very near the zero level set, as expected, as designed. And if you add on this plot the extent of the support of the detail field, you can see that indeed the perturbation only happens in this area. And if you look at the norm of the gradient of our implicit function, that is to say the approximation of the local Lipschitz constant, you can see that this only overshoots 1 in details that are included in this support of the RBF field. That is to say, outside of this, you know by construction that only the Lipschitz field has value, contributes to the value of the distance, and only in this narrow band around the zero level set you need to be careful about conservativeness. So as far as comparisons are concerned, as you can see, previous methods were either focusing on the reconstruction quality of the zero level sets at the expense of regularity of the other level sets. So for instance, Siren that we already discussed, and random Fourier features is the same kind of mechanisms and a very a method that is very similar to Siren. Or other method would focus previously on having regularly spaced and regular level sets, which would converge in the end to the true sign distance function. But with those methods, you would also suffer from the low frequency bias and not recover the very detailed geometrical detail of the zero level set. While in our case, we kind of have the best of both worlds, where we both have the details of the zero level set as a perturbation and very regular field further away from the surface. So we have the best of both worlds at the cost of an increased computational time, because the computation of the RBF field already takes a lot of time, and this adds to the fitting of the neural network, which was already quite costly. An interesting thing about our method is that the detail field is only defined in the vicinity of some points that we put on the surface, so we are able to do localized detail fields and only add details to some objects in some prescribed regions to either save up on computational time or to only add a detail, a very specific detail on a very specific area. So for instance, the text on this CAD object can be reconstructed by only putting points around the area of effect and not considering the full object. So here only 3,000 RBF centers are used. Now, the question that remains is how to select the good amount of RBF centers to put to recover the details. So what is the optimal number n of RBF based functions that we should put so that the geometry stays the same? And it is a very difficult question to answer, but one way we could try to get a correct value is to first overestimate this number of centers. So for instance here computed with 200,000 centers, fit the detail field and realize that most of the RBF centers have an associated weight in the sum that is very small and very close to zero. And so that means that most, or at least a large number of RBF centers have little to no influence on the total detail field. So what we do is we simply prune them, so add a threshold to remove all the centers that have this a weight that is too small in absolute value, and then we refit with the other RBF centers. And what we are able to recover is surface that is very, very similar, so very little geometrical error, but with less than half of the total count of RBF centers. So that brings me to my conclusion. So the takeaway of this talk, I would say, is this idea of designing functional spaces that share a property so that this property is true. So in this case, what we wanted is a conservative distance field. So both that is a field that is Lipschitz, so we relied on Lipschitz neural networks, and also a perturbation field, a detail field that is limited in support to the zero level set of the geometry, and that is zero by construction further away. So we relied on compactly supported radial basis functions for that. So of course this method is not without drawbacks. So the main limitation to me is the performance of the method, which takes quite a long time for reconstruction of a full object, and also the lack of guarantees or theoretical results on the estimation of the total number of RBF centers that one would need for a given object, or the guarantee on the size of the support. So here, for instance, there is another example where the number of centers is too small to recover all the details of the input geometry, but increasing this number also leads to higher computational costs, which is already quite a limitation. So future works in this domain could include approximate but fast fitting of RBF sum of RBF functions, which could be beneficial in this case, or heuristics to better place the RBF center onto the surface and not just rely on some uniform distribution of points to only put RBFs where they would truly matter, to reduce the total number of centers and improve computational costs. And also try to do experiments and applications with those kind of dual RBF plus neural representations. So for instance, building custom ray tracers to perform robust queries on those type of representations. So thank you for your attention, and I'll be happy to answer any questions.
Thank you, Guillaume. Any questions from the audience? Yes.
Thank you for the presentation. I was wondering if you probably did, but have you tried using some adaptive sigma for each separate point that would be the distance to its level set?
Yes, I have tried to do that, to consider only the local distance from the center to its level set. The problem is that the linear systems, like the conditioning number of the linear system, quickly becomes large, and so the solve becomes very unstable, and we are not able to get any results on that. It would be a nice extension also of our work, but didn't work in practice.
Okay, thank you.
Any other question? Okay, I'll ask something. There seems to be a repeating phenomena here where you undervalue the gradient value, because you have a lot of blue there, which means your gradient is close to 0.5 or something like this. And I think you can even see that a little bit here. There's a lot of yellow. Is there a risk of creating kind of phantom singularities close to the surface or islands or stuff like this because the gradient is artificially low?
That's like it wouldn't create some like spurious bubbles on the level set, but you may have trouble with very low gradients, especially in this case where we consider a detail field. Like it's better to have a higher gradient near the zero level set to compensate for. While, like if you have a plateau, it's harder to compensate. This problem of norm of the gradient is mostly related to the sampling of points that you take when you minimize the loss of the one Lipschitz neural network. So if you concentrate your points around the zero level set, you like when there's no or like only a small density of sampled points during training, the network just gives up on like trying to have a unit norm gradient. You get something that is very flat, like you have a bias towards flat functions in general.
Okay, makes sense. Any last questions from the audience? Okay, if not, then let's thank Guillaume and the rest of the speakers of this session.